And welcome to our ninth actually AI seminar. Today we are going to introduce Elena Demomi, who is Associate Professor at the Department of Electronics, Information and Bioengineering. The talk is about shared autonomy in surgical robots.
Hello everybody, thank you for attending the lecture and thank you for the invitation and the introduction. So the talk of today is related to a possible application of artificial intelligence. In particular, my research topic has been robotic surgery since the last years. So a few words of introduction about me. So I work as an associate professor in the medical robotics and engineering laboratory in this department. And we are part, so you can see here some of our social channels which have been put on by my PhD students. We are in the Donato Robotic Laboratories, so we are located in Building 7. We have nice premises in which we are grouping all the robotic laboratories of the department. We have three rooms in which we develop robotics, surgical robotics. So we have this setup with soon 2 silver robotic arms and the mock-up of a surgical room, operating room. We have an actual surgical robot which was donated by the Intuitive Surgical Company, and this robot has been in the hospital until 10 years ago. And then we also developed some robots, we actuate catheter robots which can be performed percutaneous intervention for cardiovascular surgery. So let's start from what is some historical words about surgical robotics. So surgical robots are not into the market since very long ago. So the first surgical robot was actually an industrial robot, so a Puma robot, which was used in order to precisely position a biopsy probe within the brain. And why? Because the brain is a soft tissue, but it's inserted in the skull, and the skull is a rigid structure. So in order to precisely target an inner structure in the brain, the idea was to use this serial manipulator, which is a high repeatability, not that high accuracy, but high repeatability, in order to insert a needle. And it was only in 1985, so not that long ago. But the first robots specifically built for surgery were actually built at the beginning of the 1990, and this one was 1991. By the two guys, so one in the US was Buster Taylor, and this in the UK was this guy in the picture here is Brian Davis. And it's quite funny because I was in a program committee meeting until 1 hour ago, and these two guys were still part of the program committee. They were also commenting the paper of the young generations. And they were also asking themselves if it was time or not to leave the stage to younger researchers. So it was nice because they were still active in the field. So not that long ago, but the market has exploded. So the applications are related to all the anatomical districts. So besides neurosurgery and orthopedics, we now have also urology, gastroenterology, and cardiothoracic surgery. And here you can see all the examples of these robots which are actually on the market. In research, now the research is moving towards minimally invasive, of course, using the Da Vinci system, and also small catheters, so small soft robots which can be inserted within the lumen of the body. So apart from this one in the lung, for perform biopsy of the lung, some examples for cardiac surgery and luminal procedure, for example, this one, are capsule robots which can be inserted in order to perform diagnosis, so also small treatment, or magnetically actuated capsule robotics which can be inserted in the lumen of the patient. In the meanwhile, the surgery has also evolved. So from the surgery of the past, in which the surgeon was performing the operation according to his own experience, his or her own experience, the surgical, so one important milestone was the introduction of medical imaging. So with the introduction of endoscopy, we can perform operations within the body, inserting a camera within the body, avoiding the need of opening entirely the patient. So this approach, which is the current approach, sees the surgeon equipped, for example, with robots, with some digital system, but yet 3% of surgical operations end up with possible complications. So the surgical room of the future will embed more sensing system in order to increase the safety of the operation. And how? For example, using the data, so the actual data of the operation, so coming from sensor, or for example, the clinical information related to the patient, in order to provide increased assistance to the surgeon. How can it be done? Well, we need an intermediate level, which is the interpretation of this information, and the interpretation should rely on the knowledge. The knowledge can be factual knowledge, so the knowledge from clinical guidelines, for example, and also practical knowledge, which can be retrieved during the operation, so during the practice. But what is the main aim? So if you understood the previous point, the main aim is to increase safety, so decrease the possibility of having complications during the operation. So let's see what happens here in this video. Okay, now it was a beeping, and then there was a crash. So I don't know if you managed to hear it. So the alarm, okay, it's actually before the crash. So what does it mean? That there is a safety system on board the camera which can detect the event before it happens. So the same way we can do the same principle, we can apply the same principle in the operating room, because we have a sensing system in the operating room. The autonomy, so this so the industry of automation has been applying autonomous driving cars, and the level of automation has been classified in 5 levels, from just providing some assistance, so like the one that you have just seen in the video, to fully automation. Fully automation means that the driver can close his eyes and takes the hands off the wheel. The problems are related to this conditional autonomy level, in which the driver can be distracted because he relies or she relies on the autonomy of the car, while instead there should be always some situations in which the decision of the user is requested. But what is the system that we are playing on with? It's the surgical robot. So this is an example of one of the most spread surgical robots. It's a Da Vinci system. It's made by 2 components, a leader and a follower. The surgeon is sits down at the leader and manipulates through some joystick here different arms. Different arms equipped with dexterous robotic surgical instruments, and one of the arms is handling the endoscope, which is a high definition, high resolution stereo endoscope, so with 2 images, one per eye, and these are what the surgeon is actually seeing. So these are 2 possible tasks, suturing and clipping, and you can see that the environment is really unstructured. It's difficult to be understood what are the regions that the surgeon is actually intervening on. You can see there are some reflections here from light, because one of the channels of the endoscope is to provide light. And also in some tasks, the surgeon is, for example, burning tissue in order to cauterize tissue, and you have smoke. And the smoke can also occlude some parts of the scene. So it's a complicated matter. But still, we can have high level of autonomy also in robotic surgery. So from no autonomy, so the surgeon is totally in control of the operation, is always in control actually, but we can increase the level of assistance of the robot until we reach a fully autonomous system. In the talk of today, I will focus my attention on these three possible levels of autonomy. So, artificial intelligence is providing some type of assistance to the surgeon. To see this picture, we have on the y-axis the difference, so increasing level of autonomy. On the x-axis, we could think about time. So here is the current situation, and here is the future situation, and you have different icons here representing possible robotic applications. And if you see, there is an increase of applications with higher level of autonomy expected in the future. So this is where the market is growing and also the research is growing. What are the issues in handling such type of data? So that, as you can see in the previous slide, the data are, for example, the imaging from the endoscope. So what are the issues in handling those data? We need a technical infrastructure for acquiring, storing, and accessing those data. We need data annotation and data sharing, and we need data analytics. So in particular, in case of endoscopic images, we are thinking about a huge amount of data. So, for example, a surgical operation can, for example, need 5 giga of data in order to store the video. And also this video, if you want to exchange this video and to assure interoperability between two, for example, two centers, you need also a large bandwidth to transmit all this data. The problem of annotation and the problem of starts from collection. So if we are talking about personal data of patients, so it's clinical data, and they are protected, they cannot be, let's say, transmitted and used without the patient consent. Data annotation problem. So we need, besides annotating the data, we should also include the possible outcomes on some clinical variables which should go with the data, because you want to correlate possible clinical data with the possible outcome of your surgery. Then we need to understand that we could have different forms of annotation, for example, spatial annotations, which we identify the position of the surgical instrument, or for example, temporal annotation, in which we code the different surgical steps, because in time the surgery is including different steps, different possible tasks that are performed on the tissues. The possible caveat in storing this amount of data is that data should represent the entire spectrum of possibilities, and there is also the problem of sharing this data. As in the computer vision community, also in this application there have been established some challenges. For example, there is this endoscopic vision challenge, in which annotated data are made available to the researcher, and the data are made available together with benchmark measures, and researchers can test their algorithms on these data which are made available. And the data analytics problem, so we need to guarantee that our systems are robust and generalizable to unseen situations, for example. But as I said before, we are dealing with clinical data, so personal data of patients. So we need to take care of different principles. So the first one is the fair data usage, which is being asked by the European Commission, for example. In all the European projects, you need to explain how you're going to make your data findable, accessible, interoperable, and reusable. So it means that if you're storing your data in some repository, for example, your repository should be findable by the other researcher, and your data should be properly explained for another user that wants to use your own data. Then we have the protection. So in Europe we have the GDPR, so we need to guarantee that there is no leakage in the data are stored properly, and there are no possible ways of losing those data, but the same is applicable in US and UK with other regulatory aspects. And also we are dealing with the software as a medical device. So we need to comply with the new MDR regulation which has been established in Europe, which guarantees the safety and the performance of all the software on the medical device. It means that you need clinical trials in order to prove the effectiveness of your device. This has slowed down the approval. So in 2022, there were 8,000 applications, but only 2,000 authorized products. What has been seen recently is that a lot of medical technology companies prioritize the market in US and China with respect to Europe. And some states like Switzerland are planning to recognize FDA instead of CE mark, claiming that they are searching for the prioritization of patient care. So there are some controversy and we need to solve this. What is the situation in the US? In the US you can go to the FDA website. So there is a huge database of all the artificial intelligence-based devices which have been approved. What you can see here is that, as you know, in FDA you can have different type of approval. And for example, there is the de novo pathway, pre-market approval, but also there is this pre-market notification. Pre-market notification means that if you want your device to be approved, you just need to demonstrate that your device is equal in terms of performances to an already approved device, and then you get the approval. And you can see, if you can see, this is the symbol, and a lot of these medical devices embedding artificial intelligence have been approved in this way. In the same website, you can also find some statistics about the artificial intelligence devices in the recent years, which have been approved in recent years. But this line here represents the sample size of the studies. And you can see here that it's been increasing, but then it has reached a plateau, and now it's stabilizing. So the sample size used to test medical devices embedding artificial intelligence is not increasing. So they decided that there is a sample size which is sufficient. So let's see some examples of our research in this context. So the big picture, which I decided to call it context awareness. So this is what our endoscopic images provide to the surgical robot, and to the surgeon, a sort of context awareness. What are the tasks that we can perform? So I think that you know about some, let's say, basic tasks that you can do in computer vision. First of all is detection. So there is a region of interest which is automatically detected. It's just a contour of a possible region of interest. Segmentation. So there is also the contouring of that a particular region that has been highlighted in the imaging. Classification. So apart from detection, you also assign a tag to the region of interest. And also we can perform, just playing with the images, we can also perform 3D reconstruction. To do what? So the main applications are decision support. So we are helping the surgeons in making decisions during the operation, during the diagnostic or treatment phase. We can provide some sort of assistance, or we can implement a better surgical training. And these are the use cases that I'm going to really be fast in trying to have just a few hints about all these possible use cases. You can see here that I also reported the level of autonomy. So in some cases we have level 1, but we can also reach level 3. In level 3, we have that the system is autonomous but needs confirmation from the surgeon. So let's start with the first one, is colon cancer endoscopy. And in this case, we are performing detection of the region, classification. We're aiming for a decision support system to perform a safer intervention. So what is colon cancer? So it's a pathology which affects 1 over 20 people. And, these are the numbers from the statistics. But we know that if the cancer is detected at early stage, it can be, so the patient doesn't have, the patient has a good prognosis. What does it mean? That there are screening procedures, so starting, so for elderly patients, there are screening procedures, so colonoscopy made as a screening, in which the endoscopist is searching for particular spots, so polyp in the colon. This is a certified product from Medtronic. So this product has achieved the FDA approval, and it's embedding artificial intelligence. So these green region of interest are automatically computed by the system, so that the system is claimed to decrease the possibility of mistakes by the endoscopist. The endoscopist is in charge of deciding whether to remove, so to perform biopsy or not on the region, but there is an alert from the system to the endoscopist. What are we doing now in the lab? So we are adding some features to this possible smart endoscopy. So the first part is that apart from detection, we are also performing classification. So not only we are highlighting the possible suspected region, but we are also adding a tag which classifies the tissue according to possible class which has been defined by the clinician. The number, as you can see here, is the level of confidence that relates the region of interest to the particular class. So the project has been is receiving the funding from the Next Generation EU. So it's one of the ecosystem that has received funds. And we want to move forward and to include our artificial intelligence in an existing system, so in a system which has been made by Atlas Endoscopy, which is a UK-based company. And in this system, the endoscope, so this is a colonoscope, it's not passive, but the head, so the camera of the endoscope is active, and it's manipulated by external magnets which are attached to a serial robot. So the external magnet can tilt the camera so that the endoscopist can see also, for example, regions which are folded and detect all the missing spots. Why this system needs artificial intelligence? To provide navigation. How? So first of all, we can use the images that are acquired with the camera to reconstruct the shape of the colon. In this way, we can also reconstruct, for example, we can detect if there are missing spots. So those missing spots are regions which the endoscopist has not seen, and might entail, for example, some dangerous regions. So if the endoscopist is going back and see that there are some missing spots which have not been reconstructed, can come back and detect and see whether there are some suspicious regions there. The second thing which has been asked by the clinician is to mark regions, so to have the possibility to come back, so to have a double check of some regions. So this is how the system works. You see that the magnetic field is also giving the position to see also, for example, these are the faults that need to be explored in order to detect whether there are polyps or not. What are the problems that we are currently facing? It's the need for annotated data. Because who has the expertise for annotating data? For sure, we need to have the clinicians, and a PhD student, they provided the clinicians with this annotation tool, which has been installed in the computer at the hospital. But we need the expert, for example, in this case, to identify some regions, and then, for example, master students or PhD students can propagate the annotation, and then the expert should supervise the annotation. But this is the only way that we can collect a data set that can be then robustly used in order to perform, for example, navigation of colonoscopy. So, how can we make the annotation process more efficient? Some suggestions have been made, for example, to introduce annotation curricula within the residency. So in medical, for example, medical courses, to ask students to annotate data. So let's go on with another example of the usage of artificial intelligence, and again, we can classify the surgical instruments to help the surgeon during this type of intervention. These interventions are intervention of microsurgery. So So the surgeon is actually operating on very small parts of the body, and the camera is a microscope, so that maximizes the magnificent the vision of the surgeon operating on, for example, nerves or small vessels. In this case, getting the images, we are able to identify the surgical instrument. The problem here is that in order to move the endoscope, so to see better what the surgical instruments are doing, to see better the actual location of where the instruments are interacting with the tissue, the surgeon has a foot pedal tray. And this distracts the surgeon while doing the operation. So our aim is to provide an autonomous system, so that's why we have level 2, which can move the camera in an autonomous way in order to provide a more ergonomics to the user. So the system has been developed together with the neurosurgeons in Humanitas, and now we are working with the company in order to embed this control in their system. So the problem of data annotation, so we need to have high quality annotated data. So more than one expert should annotate the same data set. One possible solution is to, for example, generate fake data, for example, using generative adversarial networks, because some data are already annotated, and then we propagate, we increase the data set playing with the guns. Another problem, another issue in annotation is that, for example, the expert annotating the data should choose from a restricted vocabulary. Otherwise, we lose interoperability of the data set. So for this, there is a consortium which is called SNOMED-CT, which is developing ontologies related to the medical field. SNOMED-CT is the largest one, it's a large initiative for developing ontologies for the healthcare, and we have different concepts we describe with a precise description, and also as an ontology defines the relationship between concepts. For example, here there is an example about viral pneumonia, where the virus is the causative agent, there is an anatomical location, so a finding site, and then the infective pneumonia is a respiratory disease. And this is done for a lot of pathologies, a lot of, let's say, clinical problems. And it's open, so you can, if you want, you can access and use this information. So ontologies can be used to standardize the process of annotation, because it defines a language and defines relationship between instances. So let's see where we used ontologies and why. So this is again a robotic procedure, it's a nephrectomy, so there is a tumor in the kidney which is removed using the robot. And what we did, we retrieved a lot of videos related to the procedure. The procedure is quite standardized, so these are all the different steps of the surgery. And a student was actually a medical student who was pursuing a degree in computer science, spent a lot of time with surgeons annotating each single frame of the operation using this annotation tool, in which every frame, so they were annotating the entire frame, not a region in the frame, but all the frames were annotated according to the anatomical location, the instruments used, but also how long the instrument was used. And so using an ontology which was specifically built for this occasion. Then we combined the approach, so the standard computer vision, so bottom up with the neural network analyzing every frame, but also top down. So we use also the ontology to recognize the surgical phase in the sequence of images. And we achieved a pretty good classification capabilities, and we were also able to design this pathway of surgical step within the surgery. So what could be one of the possible applications of this technology? So we are able to identify phases. So this system could be also, for example, be used in training. So to teach to the practitioner different, so the surgical steps and the surgical sequence that they have to undertake. But also, there are some other applications. For example, the control of the robot could change according to the surgical step. So the recognition of the surgical step is of utmost importance. We will see later on another possible example in using the recognition of the surgical step, which is this one right now, in which we are performing robotic prostatectomy. So we are not removing the kidney anymore, but the prostate. This intervention is really delicate because the prostate is close to the reproductive organs and also to the urinary tracts. So the surgeon has to pay attention not to damage any vessel or any nerves in the region. The idea here is to use the images in order to overlap to the intraoperative scene, which is this one, the preoperative information coming from preoperative images. In this image, you can see there are some organs which have been segmented and 3D reconstructed. Some other parts, for example, the lymph nodes, can only be seen with particular type of imaging, but we can identify the presence of lymph node in this preoperative space, and we can register, so to compute the transformation between this space and the intraoperative space. How can we make this information a 3D information? So not just a 2D image, but a 3D space. Because those two images are stereo images, so there is disparity between the two of them. Using the disparity information, we can reconstruct the scene as a point cloud. So now our surgical environment is a 3D environment made by points. We can also segment, so highlight, for example, the surgical instrument or for example, an anatomical structure in order to implement the registration between the preoperative space and the intraoperative one. And so this is the process. Again, the disparity computed using artificial intelligence and 3D reconstruction. And this is the idea one of my PhD students here. So not only let's register the 3D space, the preoperative 3D space into the intraoperative, so to have augmented reality on the surgical field. But let's also provide some information about the distance of the instrument from the region. And this structure is changing color according to the distance from the surgical instrument. So these are the lymph nodes, which can only be seen with the particular imaging type. But what is the next step? So we develop the technology, we can integrate the technology in the surgical robot, but what's next? As a biomedical engineer, we need to prove the effectiveness of our technology. So that's why we wanted to start a clinical trial. So in order to prove the effectiveness, you need to separate the population in some patients who are undergoing standard surgery and some other patients who are undergoing our, let's say, augmented reality surgery. So this is a study that we want to start soon with the European Institute of Oncology. So the last example is robotic neurosurgery. I'm just giving this example because it's level 3. So it's total autonomous system in which we have, the use case here is brain cancer. It's a rare tumor. It's really difficult to remove the brain cancer. There are different types of solutions, surgery, radiotherapy, but there is also drug delivery. Drug delivery which cannot be a systemic drug, but should be local drug delivery because you have the blood-brain barrier which prevents the drug to reach the brain. So there was this robotic catheter which was developed by Imperial College, and it's a robotic device which is able to make curved trajectories within soft tissue. So now it's moving within gelatin. So our task here as artificial intelligence guys was to plan to compute the best path to the target from a starting entry point on the skull. Another approach here, which was envisaged by one student who graduated last year, now she's working in ATH. The approach here was combining standard reinforcement learning, so with the agent exploring the environment, and the agent was the robot. So standard reinforcement learning with inverse reinforcement learning, where the demonstrations were given by the experts, so the neurosurgeons, playing with the joystick within a simulated environment and choosing the best trajectories. On top of this, the experience of the user was also coded in the form of rules using logic programming. And the two systems, so the inverse reinforcement learning was also, let's say, proposing the best trajectories to the deductive reasoning module, and the best path was eventually chosen in the end. So there was a combination of standard, let's say, so the bottom-up, so the system is learning from the experience, but also the system knowing the rules of the game through the experience of the expert. So this was the last use case which I wanted to present you. Let's see some open issues and how we are proposing to solve them. Lack of data. So what we also tried in the past was to use the transfer learning. So our networks, which were being trained on images, so for example, the Google network, ImageNet, was fine-tuned on our applications, which didn't entail a large number of data. But again, using some fine-tuning, we were able, for example, in this case, to classify laryngeal cancer. Or semi-supervised learning. So we don't have the possibility of having large annotated data sets. So this approach, which has been recently published, is including a teacher and a student network, and the teacher is also teaching to the student how to properly annotate data. But we need also to comply with the ethical guidelines from the European Commission, which regards the entire spectrum of artificial intelligence. So not only artificial intelligence applied to healthcare, which is our case. So the artificial intelligence should be trustworthy. What does it mean? Results have to be explainable. So something which is also stated in the WHO document, which says that artificial intelligence in health has to be transparent and explainable. So the results have to be interpretable by the experts. So we are providing our results to the experts, but they have to be not only to the developers, but also to the radiologists. The radiologists should understand why the network is classifying some tissue as, for example, cancer or not. There is also a relationship between explainability and causality. So in clinical settings, in order to prove that the intervention is effective, we need to understand the relationship between the intervention and the outcome. So we are not satisfied with finding correlation among variables. So if the tumor has that shape, it means that if the region has that shape, it means that it's a tumor. We need to find causal effect relationship between the patterns that we see and the outcome that we're measuring. We need some preliminary experience with explainable AI. In this case, we were using some open data sets with gene expression and clinical data. And the gene expression was transformed in images, and the classification of the patients was used using standard neural network approaches, combining heterogeneous form of data, so genes and clinical data. But this transformation in images also of the results allowed us also to interpret which was, for example, the most important clinical patterns or the most important genes which made that classification. So which caused that classification. Another possible approach in results explainability is the semantic technology, so including semantic technologies. So this is the standard approach. From data, we have this neural network approach, and then we get to the outputs. But as I said before, the top-down approach of knowledge is to codify the knowledge using, for example, ontologies. So this is the way of expressing the experience, the knowledge, so the rules of the game. Those rules can allow us to interpret the results. So the results are fed here in the rules, and those rules, through query and reasoning mechanisms, can give an explanation of the classification. And also now we are, as a group, we are trying to see whether ChatGPT can provide an explanation, further explanation, in natural language process, natural language to the user. The problem of sharing data can be solved using federated learning. Federated learning is the difference between, so when you have multi-institutional, multi-centric studies, for example, in clinical center, it's important to enlarge the spectrum of the clinical center included in a study, because you need to avoid the bias for each single center. So you're not sharing the data between centers, because this has a lot of problems about security, privacy, and so on. But you are sharing the model. So each center trains each model with its own data. And then there is an aggregation service which develop this consensus model, let's say computing a sort of a best model among all the models. And the consensus model is again sent back to the institution for further training, with the data which stays at a single institution. So as promised, I try to keep the time. So let's see some just brief take-home messages. Of course, when including artificial intelligence in medicine, we have problems which we have to pay attention to possible bias. We have the issues of certification. So not only we need to prove the effectiveness of our system, the generalizability of our system, we need also to prove the explainability, because every single component of our medical device has to be explained. For sure, we have benefits, because apart from standardization, training, and context awareness, we want to increase the safety. So in the final question, if the human-centered approach is better when we have shared and autonomous, of course, the human in the loop is always to play a role. So thank you for your attention, and I would like to thank the students, who are the main engine of all this presentation, the funding that we have received from the European Community and the Ministry, and thank you again for the time that you spent here.
Is there any question from the audience? Maybe I can ask one. I was curious about the application of reinforcement learning and inverse reinforcement learning on the brain scenario. Just wanted to know how is the pipeline. So basically, you start from the expert, then you train your agent. How does it work?
So we start from the knowledge of the environment. So the environment in our case, we have obstacles, which are the vessel. We have the target, which is the tumor. And we have the agent, which is the robot. So at the beginning, the robot explores the environment. But then we are also using some trajectories, which are defined by the user, so the expert, using the joystick. And those trajectories are combined, so the policy of those trajectories combined with the policy which is being learned through the standard reinforcement learning approach. On top of this, all the best trajectories which are proposed by the system are criticized by the deductive reasoning.
I see, thank you. Any questions?
One can discuss there.
We have our usual refreshment in the hall of the department. So let's thank again our speaker.
Please come, but technical questions you should ask to the PhD students.